Hi and welcome to video 4 of my video series on integration and how we can use integration in the Specialist Maths Unit 4 integration topic. So in this one we're going to talk about some integration of these inverse sign functions. So you remember here that we've got some rules, and our rules are, which I'll copy them from up here. Our rules are here. Actually I've got a nice copy of them here, which is from the Cambridge textbook. So if I take these down, and basically we're just applying these rules, that's all we're doing. It's nothing super special. You'll have these on your formula sheet. So the first one here is we've got this -5. Well, that 5 element just comes out the front, and the fact it's negative means it can probably be best represented as a cos inverse, but we could make it -5 times a sine inverse, so that would work as well. And I've got 16, which is of course 4 squared, and then minus x squared. So this becomes negative, sorry, not negative because we're going to make it cos, 5 cos inverse of, and we want our x over a, so in this case our x is still x, and our a is 4. And of course it's a definite integral, so it's plus c. So there's our first one. Second one, I can see there's no square root sign, so we're dealing with a tan function in this case. But I'm going to write this down as 3 out the front, 1, and I'm going to have to do a bit of playing with this in a second. So 5 will become the square root of 5 squared plus the square root of 2x squared. So I'm just building up my solution here, but I need to have it in the form of a squared plus x squared. That's what I'm working towards. But I need an a up on top here, and I don't have that a at the moment. So what I'm going to do as well, because my a is root 5, I'm going to write it down. Root 5 over root 5 squared plus root 2, I've not changed the denominator, squared, that's in the form I want now. And the integral of that, but I've got an extra factor of root 5 there, which means I need to divide by the factor of root 5 out the front. And that will make things work for me. And of course, this now means that I get 3 over root 5, and then tan inverse of x over a, which is root 2x over root 5, plus c. And we don't really like denominators with surds in them, so I'm going to write this down as 3 root 5 over 5, tan inverse of root 10 x over 5 plus c. And there's our final answer. Again, it's just applying this. So that's really a complex version, but you just have to get into that form of a over a squared plus x squared. So here's example 8, and my final example, you see it's a complex unfamiliar. So I'm going to start by determining d dx of tan inverse of ax plus b, which is a little bit trickier, but I've got a rule here for d dx of tan inverses. So if I look at question A, I'm trying to find d dx of, I'm going to try and write it like something like the rule. Tan inverse of ax plus b over 1. Now my x is just a linear function, which typically means that it's fine to do what I'd normally do, dealing with that linear function as I normally would. And so I will get from this, my a is 1, I'll get from this 1 over a squared, which is just 1, plus ax plus b squared, but I will have to multiply by the derivative of the inside function, which in this case is just a, and so that will give me a over 1 plus, now I'm going to expand this out, ax squared plus 2abx plus b squared. So I might just change my numerator, say over like that. And then I'm going to simplify this to be a over a squared x squared plus 2abx plus b squared plus 1. And there's my derivative. So I'm pretty happy with that. And I'm just following either the rule set out here with the addition of how I'd normally deal with a rule that changes from just x to a linear function. And that is by treating the linear function like it's x, but multiplying by that a as well. And there's not much more to do. It's a really simple chain rule application of this. But now, part B is asking me to calculate this integral. So what I've got, and I'm going to line this up here, is I've got the integral of 12 over 9x squared plus 12x plus 5. Now this we might not be able to integrate all of these types of terms, so this should fall into place. What we need to remember is we don't really care about the 12. If the 12 is too big or too small, we can take a factor out the front of the integral. We can fix that problem. This 5 is a bit of a problem. I need to be able to match that up with b squared plus 1 and make it work. That tells me that b squared has to equal 4. Has to, otherwise this is not going to work. Now I've also got a nice little connection here between 9x squared and ax squared, which tells me that a squared has to equal 9. So from this I get a is equal to 3, and it could be negative 3 as well, and that b is equal to 2. I'm just going to work with the positive and we'll just play around with it and we'll see how this works out. Now I've also got 12x, and this is the bit where I might get a contradiction, so I've got to be a bit careful. Does 2ab equal 12? Well, 2 times 3 times 2 does equal 12, so I'm happy with that. And you'll notice here that 2 times negative 3 times negative 2 also equals 12. So a and b could both be negative. That would also work. But as you'll see later on, that would actually just make an overall negative linear factor, which makes no difference to our tan function. So I'm just going to deal with the positives for now. So what we get then is that we get the integral of 12 over 9x squared plus 12x plus 5 dx. Well, that's equal to, now remember with our tan, when we derived this we had an a on top. So I need to leave an a on top. It's equal to the integral of 3, I'm just heading towards what I want here, 3x squared plus 2 times 3 times 2x plus 2 squared plus 1. You see that's looking a lot like what we got when we did a derivative, but we've got a 3 here now, which means I need to have a 4 out the front here. And so if I integrate this, of course where my a is 3 and my b is 2, I get 4 tan inverse of 3x plus 2 plus c. And if I go back up the top, I can see that matches with my original derivative. And that's worked out quite nicely. So it's just a case of recognizing a part A might lead to a part B, which I know most of you do, and then building a solution from that recognition. And of course, we should also recognize the fact that we did say we can't have A as negative and B as positive, because that mucks this up. It makes it negative 12, but we can have they're both negative. So we get negative 3x minus 2 plus c. That's also a solution. Okay, so that's it for integrating inverse, cosine and tan functions, and for this part of the exercise. So that should lead you nicely to 11b and 11c. All the best.